From the studios of Postscript Media and Canary Media.
I'm Shayle, and this is Catalyst. You heard it here, heat pump innovators. If you think you've got a solution that is going to work better than anything on the market today for the coldest winter night that Andy and his family are going to face in Portland, Maine, then we've got an early adopter for you. I just signed you up. I hope you're okay with that.
Oh, yeah. Talk to me in like a year. I think we'll be ready.
At long last, the era of heat pumps has arrived, is a sentence that I would like to be able to say with more conviction than I can right now.
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shayle. I'm a partner at the venture capital firm Energy Impact Partners. Welcome. The humble heat pump. It already exists in nearly every refrigeration system and AC unit in every building and refrigerator and vehicle in the world. It's the closest thing to magic that I think exists in the current energy system. To wit, heat pump efficiency is measured by a term called coefficient of performance, which basically just means efficiency. It's basically the amount of power you get out of the system relative to the power you put into the compressor. Heat pumps today have coefficients of performance anywhere from, say, 3 to upwards of 5 for really good ones. In other words, you put 1 kilowatt in, you get 3 to 5 out. Magic. It's also a form of electrification. Heat pumps, when used for building heating purposes, typically replace natural gas or fuel oil with electricity. So it's decarbonization, potentially. In some places, even in North America, it is actually a pretty mature market, mostly where those heat pumps, though this becomes a bit of a misnomer, are primarily used for cooling. So in South Carolina, for example, nearly 50% of homes already have them. But in most of the country, and particularly in colder climates, the penetration is a fraction of that. We at EIP are mildly obsessed with heat pumps. We're not alone in this, but I'd like to think we've spent more time on it than most. We've already made one investment focused on heat pumps for industrial use, more on that soon, but we're hungry to find more, particularly on the residential side. The market, despite the technology being fairly mature, the market itself is still pretty young, at least as I think about it. And I think there's an opportunity for somebody to revolutionize the product, streamline distribution and customer experience, and in the process, build a big lever for decarbonization. If that's you, get in touch with us. And when I say us, I mean me and my guest this week, which is a familiar voice for regular listeners. It's Andy Lubershane, who is EIP's head of research, my frequent macro collaborator, and as you will soon hear, our resident heat pump enthusiast. Here's Andy. Andy, welcome back.
Thank you. Happy to be back, as always.
It is finally time for us to do a heat pump episode, which we've talked about, I think, for a long time.
Yeah, I could not be more excited to talk about heat pumps. Pumped about heat pumps.
No, you get one of those. That's the only time.
All right.
All right. Let's start with quick stage setting, I suppose. What is a heat pump and why is it magic?
Yeah, so heat pumps are generally sort of a less well-recognized critical building block, not just of the energy transition, but of the modern world that we live in. Every refrigeration system, every air conditioning unit, and every building, cooling system, vehicle, all the stuff in between requires a heat pump for the most part today. And the way they work is they use this process called a vapor compression cycle, where they use a refrigerant gas, and there's dozens of different refrigerants out there, and they basically compress that gas and then they expand the gas. And as the gas goes through these phase changes, in one environment it absorbs heat, and then in another environment it dumps that heat. And the goal is to move heat from one place to another. And the magic of a heat pump is basically that If you're using an electrically driven heat pump, which is the vast majority of heat pumps today, you take a unit of electricity, like a kilowatt hour of electricity that you put into the heat pump, and you can move more heat from one place to another than a kilowatt hour's worth of heat. So you put in a kilowatt hour of electricity and you move, say, 2, 3, 4, 5 kilowatt hours worth of heat energy from one place to another. And so it's in this way they achieve what people would call more than 100% efficiency, because if what you're trying to get is heat from one place to another, you're getting more than 1 unit of heat for every unit of energy that you put into the system.
Which you might think, like, isn't this true of all energy generation systems that we use? But it's not. Actually, you're not, like, if you're burning coal, for example, you're not getting more energy out than you put in. You just happen to have this super concentrated source of energy in the form of coal, which you can afford to lose a little bit of in the process of turning it into electricity.
Right. Almost everything else we do with energy basically has efficiency losses. Like you're taking some form of energy and you're making it more useful in a way. And by making that energy more useful, you lose a little bit of the primary energy that you begin with along the way. And because of thermodynamics, and it's been a while since I've taken a physics class, but because of the principles of thermodynamics, if all you're doing is moving heat from one place to another, and because of the magical properties of these refrigerant gases, you can actually do so with higher than 100% efficiency in terms of the heat that you get from one place to another.
Right. Okay. And we'll probably talk more about, well, we're definitely going to talk more about the refrigerants because that's sort of an issue. We'll talk more about the efficiency, which is also in the heat pump context deemed the coefficient of performance or COP of a given heat pump. But as you said, heat pumps are not an immature technology. They're ubiquitous in our society, though you wouldn't know it necessarily. So why are you and I and a bunch of other people so excited about heat pumps as we think about decarbonization?
There's really two reasons. One is because of the challenge of cooling and decarbonizing cooling. And then the other is because of the challenge of decarbonizing heating. And again, because of the way heat pumps work, heat pumps are used in both of those functions. And the need for better heat pumps in those different functions is actually quite different. So in the cooling world, where heat pumps are extremely widely deployed today, whether you're cooling a space for air conditioning or whether you are refrigerating or even freezing a space, to keep something very cold, like the cold chain for food or medicine, the challenge is mainly around the pace of growth. So air conditioning demand is one of, if not the absolute fastest growing sources of electricity demand globally, and is predicted to continue to be so for decades to come. And that's for two reasons. One is because the world is getting richer. Hopefully, it will continue to get richer. And one of the first purchases that people tend to make as they ascend to the global middle class is air conditioning. And that's going to be even more true in the global south, where it's hotter and more humid than it has been in the global north, which is already relatively rich and has fairly high air conditioning penetration. And so basically, as people in hot, humid climates get wealthier, they're going to buy more air conditioning, which is a great thing because air conditioning is awesome. And obviously, we all really like it. But the challenge is that, depending on what forecast you look at, in a sort of business as usual technology scenario, that means we're on track to add, roughly speaking, another whole US electricity sector worth of electricity demand globally for this new air conditioning demand by around 2050. And then the second compounding problem here is that demand for air conditioning is only going to go up with global warming. In every climate condition, right? Because the world is getting warmer, and no matter what we do about addressing emissions today, that's going to continue to be the case for decades and decades to come because of the warming we've locked in already. And so the challenge for air conditioning, the main challenge is just keeping up with demand. And one of the issues that we've seen historically is that in the air conditioning space, consumers, by and large, focus on upfront cost, on sticker price. And not so much on efficiency and performance. And I'll be honest that I don't 100% know all of the obviously. I'll be honest that I don't really know exactly what's driving those purchasing decisions, but it's a phenomenon that is consistent across markets and geographies. That if you look at the availability of higher performance air conditioning systems in almost any country in the world, in general, consumers are, for the most part, buying the cheaper, lower performance systems today. And so it's not simply a technology problem, obviously. There's a market and an economic problem here as well around air conditioning.
Okay, so talking about cooling, I think to your point, this is where heat pumps they already play a big role, right? There's already in a lot of air conditioning systems, they already have a heat pump in them today.
Just about every air conditioning system, right?
Yeah, exactly. So it's not like this is like a brand new market for heat pumps, though as heat pumps get better and more efficient, potentially it can provide an advantage as we add a lot more air conditioning. But the challenge, the high level challenge that you're describing is that undeniably and hopefully demand for air conditioning is going to be growing fast. But that doesn't mean that demand will go for the most efficient form of air conditioning, the highest performance heat pumps, for example. And as a result, it might induce more energy demand growth than we ideally would want, which then, causes this set of questions around how are we going to supply all the power and feed all this air conditioning.
Right. The challenge in cooling I would characterize as essentially how do we make more efficient units cheaper so that people buy the more efficient units?
Right. Okay. And so that's the cooling side, but I think that's where there's like a little bit less kind of novelty from a heat pump perspective, because again, this is not a new thing. On the other hand, in heating world, heat pumps are less ubiquitous by a long shot today than they are in cooling. So talk to me about heating.
Yeah. So obviously today, the way we heat buildings, the way we heat water, in the vast majority of cases in northern climates where it gets cold, is we burn fossil fuel. We burn natural gas predominantly in North America today. In many parts of the country and the world, though, we still burn, fuel oil. And part of the reason is because the equipment is relatively cheap. A furnace or a boiler is a really low upfront costs, relatively speaking, in terms of installing and getting a heating system. And also because historically and continuing on through today, it's more difficult to make heat pumps work in a heating setting, especially in relatively cold climate environments. And the one reason for this is because of the differential in temperature that you're trying to move heat across. And that's a major driver of the efficiency of a heat pump. If you're trying to move heat from a 70-degree environment outside to a 67-degree environment inside, then that heat pump is going to be an extremely efficient, cooling system, essentially. And if you think about even kind of worst case scenarios for air conditioning today, say an air conditioner in Arizona needs to move heat from about 70 degrees, let's say, which is a relatively comfortable point for people inside of a home or a building, to say 100 degrees or 105 or 110 degrees outside. So that's a temperature lift. You're lifting the temperature and moving heat across about a 35 degree gradient. And that would be a really relatively tough thing for an air conditioning system to do. It would be operating in a less efficient mode. I live up in Maine, so cold climate environment. And if you think about what heating, home heating or building heating in Maine requires, there are times when it's 0 degrees Fahrenheit outside or 5 degrees Fahrenheit outside. And if I want to get myself comfortable, I need to lift that outdoor heat up to 70 degrees in my home. Or if I'm trying to heat up water for a nice warm shower, 100 degrees plus Fahrenheit. And so you just have to do a lot more work. It's less efficient to move heat across that higher gradient. Now, we do this today in cooling settings, for example, with freezers, but it's just harder to do efficiently at much higher volume. So that's one of the reasons it's been challenging for heat pumps, electric heat pumps, to penetrate the heating market today.
So one of the things that has long been the sort of knock on heat pumps, which is for heating, which is exactly what you're describing, is people think they don't work in cold climates for exactly that reason. I think it's important maybe to spend a minute talking about like what is the performance of a heat pump of a, let's just say, like a higher end Mitsubishi heat pump today. Would it work in Maine? Could you install a heat pump? Is it an economic challenge or a technical challenge?
So if you're using a higher performance heat pump today that has, features that are designed for very cold climate operations, you can fully heat a home or a building, especially if that home or building is decently well insulated, so you're not losing a lot of heat as you're pumping it into the home with electric heat pumps. I mean, and actually, heat pumps are still pretty darn efficient, even at temperatures we'd consider pretty cold. So, I would say a medium performance heat pump today, when the temperature is around freezing, 32 degrees Fahrenheit, you're probably getting around a coefficient of performance of 3, when the temperature's, if you're just trying to heat a home. So, again, you're moving 3 kilowatt hours worth of heat into the building for every kilowatt hour worth of electricity you put into the heat pump. The challenge is that there are some periods, they're not as often, but there are some periods in Maine and other northern climate areas where the temperature goes, well below zero very occasionally. And if you head up to Canada, that very occasionally is a little bit more often. And this is a sort of a phenomenon for every heat pump on the market. As the temperature outside drops, especially as it drops well below freezing, the efficiency of the unit drops. And so by the time you get to around, -5, -10 degrees, certainly anywhere below that, with almost any heat pump on the market, that heat pump loses some of its capacity. So you need a bigger heat pump that starts with higher capacity in order to heat the same amount of space. And B, just the efficiency drops tremendously to the point where you're basically doing resistance heating. So your coefficient of performance drops to 1. And in some cases, you might even have to use a little bit of energy just to keep the system from freezing up and getting covered in ice, which means you might even be less than efficiency of 1. And this leads to just another really big systemic problem for heat pumps if we were really going to start to electrify a lot of heating in cold climates, which is that during those extremely cold periods, the peak electricity load needed to service that heating demand just spikes tremendously.
Right. We'll come back to, I think, the winter peak problem, which is worthy of its own whole portion of this conversation. But first, I want to do two things. One, I want to talk about the state of heat pump adoption. Let's focus on residential heat pumps for heating, for the most part for heating. A lot of these are dual use, and you can do cooling as well. But let's talk about the state of the market and what the adoption curve looks like today. And then I want to spend some time on where we think there's room for innovation. Obviously, you and I spent a lot of time thinking about this, both because we think it's important and because we think it's an investable category from a venture capital perspective. We haven't made an investment there yet. So let's talk about what we think it would take to create a business that might revolutionize heat pump adoption. First, state of the market. Where are we in terms of heat pump adoption? And this is where when I look at these numbers, I'm reminded of electric vehicle adoption circa 2 years ago, where there was a very clear and very stark divide between what was happening in Europe and what was happening in the US. Feels pretty similar in heat pump world right now.
That's very true. And what's been interesting is heat pumps actually had a moment in the first decade of the century, so in the mid-aughts, where natural gas prices in North America were starting to rise pretty precipitously, and heat pump adoption started to rise as well. So back in 2000, at the turn of the century, heat pump adoption, for new heating systems in, say, the U.S. Midwest, relatively cold climate area was at about 5%. And by the late aughts, 2009, 2010, it had actually grown up to about 20%. And this is because I think mainly of economics, that electric heating started to look more economically attractive as natural gas heating was looking more expensive. But then, of course, in the early 2010s, we had the shale gas boom in North America. Natural gas prices fell off, and a few years later, so did heat pump adoption. And so heat pump adoption in cold climates has actually fallen now back to about that 5 to 10% range for new additions. Overall, across the U.S., it's around 40%, but that's predominantly because of another sort of magical property of heat pumps, which is that the same system can be used bidirectionally if it's designed appropriately, which means that you can use one heat pump to do both cooling and heating. And so heat pumps are now in, warmer climate regions of the US Southeast, for example, being deployed as the only system for heating and cooling a lot of buildings, or the predominant system for heating and cooling a lot of buildings. So that's the U.S. It's been a real challenge because electric heat pumps just do not look as economically attractive for consumers compared with continuing to burn natural gas. That was fairly true in Europe as well, up until just the past year, where the crisis in Europe, the Ukraine war, has caused natural gas prices to completely go through the roof. And I don't have the data in front of me right now, but everything I've seen shows that there's just a surge in consumer demand for electric heat pumps.
Yeah, I don't have this number in front of me either. I can't remember whether this is Germany or all of Europe, but in one of the two places, they installed more heat pumps, or there are more applications for permits for heat pumps in August of 2022 than all of 2021 in its entirety. Like there is an undeniable and clear inflection point happening in Europe right now, where heat pump adoption is just like shooting through the roof. Though it's an interesting dynamic there. So obviously, like that's trying to get off of natural gas and onto electricity, but electricity prices are spiking in Europe as well. So I haven't run the numbers to figure out whether this is a mathematically driven thing or whether it's more of a let's all get on board with getting off of Russian gas because we know this is going to be a problem for us until we solve it.
Yeah, I mean, of course, the problem right now is electricity prices in many European countries. Electricity, generation is still largely tied to natural gas, at least on the margin. And so until natural gas is driven out of the electricity generation sector, then when you use electricity to run a heat pump, you're actually, using that gas less efficiently, right? Because if you're burning gas even in a CCGT, maybe you're getting, 50% efficiency, and then using that electricity it's a complex problem. But yes, I do think some of this is thinking ahead to decarbonization of electric supply.
Let's come back to the U.S. then and talk about why adoption has not been more rapid, or what we could do to bend that curve upward. I think there's a couple of categories. I mean, one thing I've gotten convinced of, I'm curious whether this is true for you as well, is that for any one player, any one company to single-handedly bend the curve on heat pump adoption, it sort of has to be a vertically integrated solution of some kind or another, because as you look at what are the bottlenecks holding this market back, it feels to me like it is a combination of the product itself and the limitations there, where there is innovations to be had around improving the product, the hardware, and then the messiness of the consumer journey to adoption, which is still generally a terrible customer experience. I can say from experience myself, having installed heat pumps not long ago in my house, but this is also what you hear universally. It's one of these things similar to how dealers didn't want to sell EVs. You have contractors who don't know about heat pumps or don't want to sell heat pumps or think that they're too expensive or outdated. You've got a messy process of getting an accurate quote. You can't do it remotely yet. people, the consumer awareness is low. So it feels to me like there's a need sort of across the value chain, from building a better heat pump to figuring out how to get it in customers' hands faster, easier, and with a lower acquisition cost. Do you agree with that thesis?
I agree. Yeah, as you know, I've been trying to understand how much of this is a product problem and technology problem, and how much of it is a kind of go to market sales, financing, packaging for the consumer problem. And I guess what I've come to is those problems are actually more interrelated than I initially understood. And that's because these getting to a more efficient, higher performance heat pump would reduce some of the sales friction and would reduce some of the objections that installers and customers ultimately have to them. I mean, to begin with, if you could increase heat pump efficiency, particularly in relatively cold temperatures, without dramatically adding to the cost. So if you could find a way of you know of improving performance and driving the capex down for that additional performance, then heat pumps are just going to look on a total cost of ownership basis more attractive, more competitive relative to continuing to burn natural gas or oil. Um, and then also, if you can make heat pumps more efficient at colder temperatures, and you avoid the winter night problem that you mentioned earlier, where there are periods in the winter, and especially in the middle of the night, where it gets very, very cold, that heat pump efficiency plummets, then maybe for a higher percentage of households, you don't need to upgrade your electricity breaker box in order to install the heat pump, because you have enough amperage in that box to run the system that you're installing, even on those coldest winter nights. And that at a systemic level, as we add more and more electric heat pumps to many houses, that's also going to start to save significant cost on the grid side of the meter, in terms of upgrading the electric distribution system to handle all of this new electricity demand. One of the things that I've heard anecdotally is that if a heat pump today requires an upgrade to a circuit breaker box because it's just going to require too much peak capacity, then that adds a delay to a project, right? And so if you're an HVAC installer and someone is talking about adding heat pumps, and they also need to upgrade their breaker box, and maybe that actually requires you to go to the utility, tell them you're upgrading your breaker box, and then the local utility, has to install a new service level transformer to serve that household and a few other households around it. That's going to be a major delay on the project. And so that installer is just going to have an incentive to say, actually, you know what, why don't we just go with a furnace, a condensing boiler? It's really efficient use of natural gas. It's going to be probably cheaper for you, certainly upfront and maybe even over, the next 10 years. And we can do this project today, and I can do this project today. And so I think higher efficiency, particularly at cold temperatures, is really the key, if you can do it without significantly adding to the cost of the unit.
I think there are three solutions to that problem. This is why I'm so focused on a vertically integrated strategy. One is to improve the product, as you said. Higher efficiency at lower temperatures means you're just less likely to need the upgrade, the electrical upgrade. Two is get better at predicting who will and won't need an electrical upgrade, so that you don't run through that whole process at the start. And this is where customer acquisition cost really balloons for things like this. If you knew a priori, imagine you knew ahead of time, before you ever rolled a truck to somebody's house, whether they were going to be able to install a heat pump large enough to heat their home without needing an upgrade, you could save yourself a lot of time and cost and hassle. So that's a second component. And then a third component is, if you have installers or contractors who are really incentivized to sell heat pumps, like figure out the incentive model for them. To your point, like nobody, they're probably currently generally, if they could do anything, they're incentivized to do projects they could just do. But figure out that incentive model, have them captive, exclusive heat pump brand, whatever it might be. And all those things can sort of serve to improve that one piece of the puzzle, which is one among a bunch of pieces of this puzzle to me, which is why I think there's like a holistic soup to nuts revamp to be had.
I agree. It's really hard to disaggregate the product and the go-to-market strategy and channels for, I think if you really, really wanted to make a dent in the market for heat pumps.
Okay, so let's imagine success for a second. Let's say that heat pumps get steadily better, or maybe there's some breakthrough advance in heat pump technology. They become more efficient at low temperatures. Let's say that we figure out the downstream side and, customer adoption becomes better, customer acquisition costs become cheaper, et cetera. As a result, heat pump adoption does increase rapidly in the US, as we are starting to see in Europe, and we'll see whether that's a sustainable trend. I think then the question is going to be, have we caused a new set of problems for the grid? Because we love electrification, obviously, but not all electrification is purely beneficial electrification. It causes a bunch of side effects that you have to think about. So what would it look like to see heat pump adoption for heating in cool climates at scale here? How big a deal would that be from an electricity perspective?
Let's start with an individual house, and again, think about in a cold climate like up here in Maine, what it looks like with heat pump technology. That if you have a really, really cold snap in the middle of the winter, again, this winter night problem, and the temperature gets down to negative 15 degrees for, 8-10 hours. Potentially even longer. What does that do to electricity demand for a single house? And in short, roughly speaking, for a typical US household, it means adding new peak load to that home that's equivalent to about 2 electric vehicles that are plugged into level 2 chargers during those cold periods. And that's on top of what we hope to be an electric vehicle or two that are actually plugged into level 2 chargers at the home. And so what this might do in cold climate environments is basically shift peak demand from the summer to the winter and increase the peak by about 3x. And so, it is certainly possible that electrification is sort of a pure winning strategy, that we could find a way to stage upgrades of the grid all the way from the distribution system to transmission and build out generation to serve that new peak load. But I think it is a big challenge, even if you have, pretty significantly more efficient, compression systems and components of heat pumps that let you operate at a somewhat higher coefficient of performance at those very low temperatures. And so I think it is worth noting that the goal here is not necessarily, pure full electrification. The goal is dramatic levels of decarbonization, of which electrification is probably going to be a big part of that strategy. But, as you and I have talked about on this pod before, it may be the right answer to continue to consume some amount of fuel, maybe even natural gas, in home and building heat. It might turn out to be one of these end uses of energy for which continuing to consume some fossil fuel at lower quantities is the right long-term strategy for decarbonization. One way of doing that we've looked at and spent a lot of time at EIP actually is thermally driven heat pumps. So you can drive this vapor compression cycle. You can make a heat pump that runs on heat from combustion. So you can burn natural gas, for example. You could burn renewable natural gas. Down the road, you could burn some amount of hydrogen in a heat pump to basically create a heat pump that both uses the energy from the fuel to heat the home, as well as is able to absorb some energy from the outdoor environment to heat a building as well.
Yeah, I think for me, the bigger point is I think there's enormous progress that's extremely exciting being made across an array of different sectors to decarbonize them via electrification, whether it be light-duty passenger vehicles, which is maybe the furthest along, to some industrial processes directly electrifying, to creating things like green hydrogen via electrolysis or doing direct air capture, right? And this is one of this being heat electrification, building heat electrification, I should say, is one among that list to me, and what potentially one of the bigger ones, one of the ones you could imagine scaling faster. But when you look at all of them together, you start to realize that one, electricity is going to be a great business to be in for the next couple of decades. Like demand should be growing undeniably, which it has not really historically for the past couple of decades. Though we went through a period 40, 50 years ago where it's 10% annual growth. Now we're down to 1 or 2, or we have been recently. So, load growth curve increases again. Like I don't see any way in which that doesn't happen. But it also, I think, means to me that we're going to be kind of stressing the limits of what electricity can provide in lots of different ways. We're going to be testing the limits of our ability to transmit electricity over long distances. Testing our limits of how much reserve capacity you need to have online to serve that cold winter Maine night that you're describing. We're going to be testing all these edge cases of what happens when you have too much uncontrolled EV charging simultaneous with a cold night and, some industrial load that can't turn off in the vicinity. And this is all going to be sort of locationally specific, but in aggregate, to me, every one of these incremental large areas of electrification adds to this kind of bursting at the seams image I have in my head of electricity over the next decade or two.
I agree. And I think that one of the big question marks in how we're going to decarbonize in the energy transition is what electrification really costs at that kind of scale, which we just don't really, it's very hard to study today. It's very hard to say, what does it really cost to build out every aspect of the grid to serve, 3x higher peak load than we have today or more? We have pretty good studies and estimates of what incremental levels of electrification cost, marginal grid expansion and upgrades to distribution lines and substations like that is doable. Although even in that case, there's a really wide range and it's very site specific. But at a macro level, what does electrification cost at that scale? We don't really know yet.
All right. So you're an interesting case study here, because on one hand, you're definitely an early adopter and you're a heat pumpophile. On the other hand, you live in Maine. So do you have a heat pump right now?
I have oil heat in my home, unfortunately, which I'm really embarrassed to say, but that's due to idiosyncratic reasons about the house. And we only moved in 2 years ago, and I have this big plan to trick this thing out completely when it comes to energy, and probably want to do it all at once. But no, currently I burn oil and sometimes wood. We've got a wood stove, but
all right,
no heat pumps.
You heard it here, heat pump innovators. If you think you've got a solution that is going to work better than anything on the market today for the coldest winter night that Andy and his family are going to face in Portland, Maine, then we've got an early adopter for you. I just signed you up. I hope you're okay with that.
Oh yeah. Talk to me in a year. I think we'll be ready.
If you're going to wait a year, who's going to do it faster? If not you, then who? If not now, then when, Andy?
Well, all right. Talk to me in 6 months, and me and the family will discuss.
All right. Fair enough. All right. Thanks for coming on. Excited to talk heat pumps with you behind a microphone rather than just as we normally do everywhere else.
Likewise.
Andy Lubershane is the Managing Director of Research at EIP. What did you think? What did we miss? Let us know. If you care about heat pumps, if you have a heat pump, if you don't have a heat pump, tell us about it. Tell us why. Find us on Twitter at @CatalystPod. You can find me there too. If you like the show, as always, go over to Spotify or Apple Podcasts and leave us a rating and review. This show is a co-production of Postscript Media and Canary Media. You can head over to canarymedia.com for links to today's topics. And as always, Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and ag, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Daniel Waldorf and Dalvin Abouaji, mixing by Greg Vilfrank and Sean Marquand, theme song by Sean Marquand. Our managing producer is Cecily Meza Martinez. I'm Shayle Khan, and this is Catalyst.